This is the second training video for Terracon's GINT CPT system. I'm assuming you've already watched the first video and have a basic understanding of how to import CPT data, process it, and print deliverables. This video is going to touch on how to import and print results for seismic shear waves, dissipation tests. We'll touch on how to change settings for the CPT reports, and a few other ways to print CPT data. More specifically, we're going to touch on each of the items listed here. First, let's talk about shear wave velocity measurements. Now, GINT does not have the capability to take the raw shear waves and determine the shear wave velocities with depth. You're going to use a program such as the default Vertex software or SC1RAV, something along those lines, to determine your shear wave velocity averages with depth. Once you do that, you can have a spreadsheet such as this with your depth and your associated shear wave velocity measurement. Now, if we jump over to GINT, you can see I've already created a basic GINT project, imported CPT data, and added some of the project information. I've got 4 CPTs in this case. One of them included seismic shear wave velocity measurements. To add those, I'm going to click on my CPT table and then my CPT S-wave velocity tab. You can see I have no measurements for any of the tests yet, but if I click on the SCPT-1 and copy my data from the spreadsheet and paste it into GINT, it's as simple as that. Here's an example of a log with shear wave velocity measurements. If you enter the data as I just showed you, it's going to automatically show up on your default CPT log. There's also a way to print just a graph of your shear wave velocity profile. To do that, when we go back to output, and instead of just printing your typical log like you normally would, let's go to graphs. There are several options to print graphs. We're going to choose the CPT shear wave velocity option. Only one of our tests have data, so that's all it shows up. And we would just export it to a PDF as normal. And when you do so, it's going to print a graph that looks like this. Next item on the list is how do we identify and remove rod breaks. Rod breaks are artificially low measurements that occur in the field when the operator stops the forward progress of the machine to add an extension rod. And I've included an example here with a few rod breaks. You can see there's a very thin 1 or 2 measurements low layer, and that corresponds in both tip and sleeve and corresponds to a push rate of 0. So we can identify that this is in fact an artificially low measurement and does not reflect actual subsurface conditions. Now you can go into the CPT data table and manually identify and delete each of these, but that's obviously pretty time consuming. So we've developed 2 methods to identify and delete rod breaks. The first is to do it during import. As you've already noticed, a dialog appears asking you if you want to search for rod breaks during import. There's a second way to do it, and that's after import in the add-ins menu. It's a little bit slower because you've got to go through each test individually, but this has a big benefit in that you can already have had your log printed out. A good idea is to do what I did here, print tip, sleeve, and push rate, and that way you can be sure that you are deleting actual rod breaks and not just soft, thin layers that are a true reflection of the subsurface. So if we jump back into GINT here, I'm going to demonstrate both of those options. First, I'll demonstrate the during import option. Import the CPT data as you normally would. And your typical overwrite options, it tells us we have English unit selected. And this is the window I mentioned earlier. Do we want to search later for rod breaks, or do we want to do it right now during import? The recommended way is to do it later, as we talked about. But we can do it now. If we click search during import, we get these windows that tell us that there's a low tip measurement at 1.64 feet. Do we want to delete it? We can click delete all, and it won't ask us anymore. Anyone that it identifies is automatically going to delete. Skip this one, and we could skip all of them. In this case, let's just go ahead and skip all. So this is the test we just imported, and any apparent rod breaks we deleted during import will no longer be in that test. Now the recommended way, as we mentioned, is number 2. That's to import your test as normal, print a log such as this, and then go back to the CPT table, click on the test you want to search, and click down on the CPT data. At that point, we can go into the add-ins menu and click search for rod breaks. We get the same window, and it tells us there's a low measurement at 10.24 feet. It looks like it's a rod break. We can look at the log and determine whether or not we think that is a true rod break or just a soft, thin layer, and delete it or skip it as is necessary. Let's delete it, delete this one, and skip the rest. It tells us how many were deleted within that test. And as I mentioned earlier, we have to go through each test with this process, but we can be sure that we're not deleting any true reflections of the subsurface. And that brings us to the third item, which is dissipation tests. Here's an example graph, an example output of a dissipation test. Dissipation test, as I'm sure you're familiar, is just when you're running a CPT, you stop at a given elevation or depth and let pore pressure go back to 0. This is helpful in fine-grained materials and can help identify things like your CV value and things like that. So if we jump over to GINT, I'll show you how to import a dissipation test. As you know, there are separate files for your regular CPT data and then a dissipation test. Let's do a Hoagland toggler in this case. And select your test to import. Overwrite options again, and system of units. We've imported 324 measurements. Now, if you've already have imported regular CPT data for that test, it won't add an extra borehole or test identification number. But in this case, we hadn't had that in there, so it goes ahead and adds BVS-102 with a termination depth and date. To look at our dissipation data, we can go back to the CPT table and the dissipation test tab. You can see we actually, in the field, conducted 3 different dissipation tests within BVS-102. So at 16 feet, we can look down here and see our measured pore pressure with time. Oftentimes, it's helpful in calculating some of our parameters, and just an easier way to present data uniformly to calculate your normalized excess pore pressure, which takes your peak measurement and assigns it as 1, and everything below that is proportionally down to 0. To calculate that, we're going to trigger it by entering a water depth. You'll notice a pop-up at this point tells you that your initial measurement is that, and no override was entered. Oftentimes that's okay, and we're going to continue. Sometimes, however, as is the case at 22 feet here, your dissipation test is actually going to climb before reaching a peak, at which point it's going to descend back down to 0. This occurs especially in fissured clays and is a normal reflection of the data. So what we want to do at this point is to identify the actual peak, 0.26, and we'll enter that as an override. And then once we enter a water depth, it'll calculate my normalized excess pore pressure. And I can do that for each of the measurements. So now we've got all of our excess pore pressure and data entered. It's time to go ahead and output our deliverable. Again, we're going to jump to the graphs tab as opposed to the logs. And we select which type of graph we want to export. You'll see two options for pore pressure dissipation: to plot it on a log, a semi-log graph, or a time versus or square root of time graph. In this case, let's just do a log-based graph. We can go select each of the tests and click export. And once you do that, you'll get a graph that looks like this. Let's select the place we want to save our PDF and hit export. And you'll see this window pops up with a few options. Number one, do we want to print raw pore pressure measurements or our normalized excess pore pressure? And secondly, do we want time to be in minutes or seconds? You can select to show your exhibit number on this graph as well, which is going to default to B-1. And there we have our graphs. You can see included is the test identification number, the depth, and the total duration of the dissipation test. Next item on the list is customizing our correlative parameters. You'll recall from the first video that we have two basic types of CPT reports. We have our standard report. That includes all of our ASTM required data. That's the log we're going to include in all of our projects and all of our reports. And then we have the correlative parameters report, and this gives the practitioner some flexibility to present some other parameters, measured items such as tilt angle and push rate, and also the correlative parameters like shear strength, OCR, friction angle. So if you just print your default correlative parameters, you don't go in and customize anything, these are the 5 items you're going to get. But we can go in to the CPT report setup table and choose up to 6 customized parameters to print. We can also choose as few as 3. In this case, you can see N60, push rate, and relative density. And these can be included in any order, and they are independent of your material description, soil behavior type, and an adjacent boring graphic. Your material description will always display on both your CPT standard log and your correlative parameters log. And anytime you identify an adjacent boring, that's also going to display. Now your correlative parameters, you can go in and choose from these 20 items. You'll notice some of them are actually measured. You can choose to display those, but many of them are calculated based on published formula. And just a reminder, it's important when we are doing projects that include CPT to include a description of what a CPT is in our field exploration description. This is a Word document, can be tailored to the client. And also to include our CPT general notes page, typically in Appendix C. And this just references the formula we used to determine the correlative parameters and the relative reliability of these correlative parameters. That way we communicate to the client where we're getting our data from and how reliable it is. So let's jump over to GINT and show how to customize our correlative parameters. We go to our CPT table and our CPT tab. Once we hop over to the CPT report setup, you can see we have 6 fields here for correlative parameters. On default, they're going to be blank. If they're blank, you're going to print the default correlative parameters log I showed you a second ago. But the practitioner can go in and identify as few as 3 and up to 6 parameters to show on the correlative parameters report. So you can see you can customize that as needed. And now when you print your CPT correlative parameters report, it's going to show pore pressure on the left, followed by unit weight, vertical stress, and OCR. And while we're in the CPT report setup tab, there's a lot of functions within this tab. This is your maximum and minimum overrides. The GINT system is going to identify and assign a maximum based on the measured data. But if any time you want to override a maximum or a minimum, this is where you would do that. You can also choose to hide your dual plots here, whether it be tip, sleeve, or N60. You can choose to hide your groundwater depth. If you don't want to show that, you're not very sure about it, you can choose to hide that in log as well as the hydrostatic plot. And there's also an option all the way at the bottom to hide your adjacent boring graphic. That would be used in the case that you want to, in the title block, assign a adjacent boring, but don't want to display the graphic on the CPT log. So that brings us to our next item, which is the adjacent boring. Oftentimes it's helpful to show an adjacent boring, to perform an adjacent boring adjacent to a CPT to get some physical samples of the soil. Here's an example of a log where the user identified a hand auger boring to 6 feet adjacent to the CPT. And you can see that in the title block, the adjacent test is identified, the graphic is displayed, and a note appears down at the bottom that says see the HAB-1 for the adjacent test's full details. And you can also see, as we mentioned earlier, that your adjacent boring is going to display on both your standard CPT log and the correlative parameters log. As we switch over to GINT here, in order to display an adjacent boring, we first need to go into the borehole tab and enter a soil test boring or a boring like you normally would. So this is not going to automatically import. We would have to type in our test name, the depth, and all the typical data. We enter sample data and soil component lithology like normal. So this is the field that the adjacent test field is going to pull from. Now, to identify it as an adjacent test to one of the CPTs, we go back to the CPT table in the CPT tab and click on the appropriate field and type in the identification number for the adjacent borehole, in this case HAB-1. It's important you type it in exactly as it appears in GINT, otherwise it won't identify it. So now when we go and print our log, it will include this adjacent material description. And lastly, there's an option within the customized correlative log to display the full lithology for an adjacent boring. So you can see it, instead of just showing the graphic, it's going to pull it over and show all of the data for that adjacent boring. To do that, we would just come back into our CPT report setup and customize our correlative parameters report to include our adjacent borehole description. And when we print our correlative parameters log, that's how it's going to show up. That brings us to CPT graphs. Oftentimes it's helpful not just to print logs of several parameters for individual CPT tests, but also to print out a graph of a single parameter for multiple CPTs. In this case, we're looking at elastic modulus for 4 CPT tests. Here's an example of corrected tip resistance for, again, 4 tests. At times, this is going to be helpful, especially site characterization projects, to provide for the client, but primarily this is just helpful for the Terracon practitioner to identify general subsurface stratigraphy. So to print these CPT parameter graphs, we go back to output, and instead of logs, we're going to hit graphs and click the drop-down menu. Again, there's several options. We can choose the effective friction angle, constrained modulus, N60, OCRs, and things. Choose the parameter you'd like to print and export that to PDF. Last function we'll touch on today is how to export CPT data to Excel. This is helpful in performing calculations for both Terracon practitioners, but a lot of times, especially site characterization projects, it's going to be required by our client. It's actually listed in ASTM as an optional requirement. So if the client requests it, we need to be able to provide it. To do this, we'll go back to the input and the add-ins menu. And you can see there's an option in that menu to export the CPT data to Excel. If we click that, it's going to ask us, do we want to open it now or just save it and close it? In this case, let's open it now. And we're going to save it just on my desktop for now. And you can see it gives us an overview of the project information in this tab, and then lists each of our CPTs with the tabular data. Not only includes measured items, but also all of our correlated parameters. And that concludes the presentation. Thank you for your time.